Myself, Dr. R Kesavulu, Associate Professor from Department of Physics, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today I am going to discuss about today topic is enhanced visible emissions of prismodium 3 plus doped oxyfluoride transparent glass ceramics. This is one of the important topic from the laser glass spectroscope. So last section and previous session was discussed on the upconversion of erbium 3 plus doped oxyfluoride transparent glass ceramics containing strontium fluoride nanocrystals. So last session we discussed mainly focused on the strontium fluoride nanocrystal. We studied the upconversion emissions of erbium 3 plus doped oxyfluoride transparent glass ceramics. What are the experimental methods and techniques and results and discussion and conclusions we are discussed in the last session. So today we are going to discuss about the enhanced visible emissions of prismodium 3 plus doped oxyfluoride transparent glass ceramics. The outline of the today talk is on the introduction of the prismodium 3 plus doped oxyfluoride transparent glass ceramics, as well as experimental methods and techniques of the prismodium 3 plus doped oxyfluoride transparent glass ceramics, and resultant discussion of the prismodium 3 plus doped oxyfluoride transparent glass ceramics. Finally, conclusions of the enhancement of the visible emissions of prismodium 3 plus doped oxyfluoride transparent glass ceramics. This also containing strontium fluoride nanocrystals. This is one of the important applications for the photonic applications we can use for the prismodium 3 plus doped oxyfluoride transparent glass ceramics. Now coming to the introduction, importance of lanthanum ions or rare earth ions. This in the periodic table we are in the lanthanide elements or rare earth elements. Among the 14 elements we are going to discuss about the prismodium 3 plus ions. This is one of the important lanthanide ions in the F black elements. This electronic configuration belongs to xenon 4Fn 5s2 5p6, that is n equal to 1 to 13 elements. So here in this one we are going to discuss about the rare earth ion plus Re3 plus we are going to discuss about the prismodium 3 plus ions. What are the optical properties of the rare earth elements? Strong absorption and fluorescence, wide range of excitation levels and emission levels. It will cover completely from ultraviolet UV to visible VIS means visible region and also infrared. So it can cover completely ultraviolet, visible, infrared regions. In infrared regions, mainly it can cover the near infrared and far infrared also it can cover. What are the important applications of the particularly rare earth or lanthanide doped elements? So it can useful for the photonic applications, that is included with the lasers application we can use, display application we can use, and sensor applications we can use, and also lighting diodes also lighting effect also we can use, and also we can medical purpose also we can use, biomedical imaging system also we can use. So different kind of applications is there. So totally we can use for the lot of photonic applications we can use for the different rare earth doped lanthanide ions for the photonic applications, particularly in the case of in our present study we are studying the prismodium 3 plus ions, that is we are going to study the prismodium 3 plus doped oxyfluoride transparent glass ceramics. Next, main introduction of the glass ceramic material. So generally glass ceramic, it possesses the two-phase materials. That is the main idea or goal of the transparent glass ceramics is it can possess the two-phase materials. That is, one is crystalline phase, other one is amorphous. That is glass in nature, otherwise crystalline nature. It should be possess two-phase materials. Next, the reason is to enhancement of luminescence of rare earth ions, increase of emissions as well as decay times. That means lifetime measurements it will be both emissions and lifetime measurements will be enhancement will be takes place whenever the glass is completely converted into glass ceramics. So automatically it can enhance the incremental of the luminescence properties as well as lifetime measurements. What are the requirements required for the to prepare the transparent glass ceramics? That is small crystal size, that is nano size particle we need to embedded or incorporate into the glassy materials. That is first one. Next other one is refractive index of the crystalline phase. So it should be have the refractive index of crystalline phase should be there. Next percentage of non-crystalline embedded in glassy system. That is very important. So how much volume, how much percentage of nanocrystals embedded into the glassy system? Suppose this completely glass system. How much of the nanocrystal? That means in the case of here strontium fluoride. How much strontium fluoride occupied in this completely glassy material? How much portion? That is very important. The percentage of non-crystals embedded in the glassy material. By using this nanocrystal, the fluoride content of strontium fluoride content. Then only whenever the strontium fluoride nanocrystals incorporated in the glassy surface, glass material, automatically we can study the enhancement of luminescence properties as well as decay time measurements. So this is the main reason and requirements of the preparation of the glass ceramic materials. What kind of materials we can use to prepare the glass ceramic material? That is a special chemical composition. So oxyfluoride glasses with fluoride based contents. Completely it should be in the fluoride based content, because fluoride based content is having the low phonon energy. Whenever the low phonon energy, automatically non-radiative decay loss will decrease, at the same time enhance the luminescence properties. That is why you are choosing the fluoride content based compounds. That is in oxyfluoride glasses with lead fluoride compound, that is zinc fluoride, barium fluoride, sodium fluoride, strontium fluoride, yttrium fluoride, calcium and etc. Different kind of fluoride content. In particular, in this study, we are focused on the strontium fluoride nanocrystals. This is in the oxyfluoride glass. If oxide glass with silicon dioxide, yttrium oxide, phosphorus pentoxide, germanium oxide, hafnium oxide. These are the different oxide-based glass systems. What are the other contents? That means fluoride-based one, chalcogenate. That is fluoride means completely fluoride content. Chalcogenate means sulfides, lead. These are the that means these are the toxic elements that we can use to prepare the chalcogenate glasses. What are the methods to prepare the glass ceramics? So universal method is called heat treatment process or nucleation process. Second one is laser annealing method. Third one is sol gel technology. So among the three methods, most of them we are using for the heat treatment process or nucleation process. Whenever the glass material we have to give the heat treatment or nucleation process, automatically we can convert the glass, the amorphous nature to crystalline nature. So that is we are going to focus in this study heat treatment process. We are prepared the glass material to transparent glass ceramics. Next, introduction of the glass ceramic materials. See, glass ceramics, GCS, that is are the polycrystalline ceramic materials formed through the controlled nucleation and growth of crystalline phase. That is very important. For the precursor glass means completely amorphous material. The glass ceramics is usually made in these two steps. First step is precursor glass made by the normal melt quenching technique. So initially we need to prepare the glass material by using the well-known method is called conventional melt quenching technique. We can prepare in this method, we can prepare the precursor glass, that means amorphous material we can prepare. After that, we need to give the other method is nucleation or heat process method. So in that one, the structural phase transition thermally induced to transform into the composite material formed by the at least one crystalline phase dispersed within the glass matrix. So crystalline phase should be there. Then only we can prepare the glass to glass ceramics. So that is we need two steps. One is we have to method prepare the glass material or amorphous material by using of melt quenching technique. Then after preparation of glass material, you need to do the nucleation method or heat process. Then only we can, that should be have the one crystalline phase. Then only we can prepare the glass ceramics. Next, mainly rare earth doped glasses and transparent glass ceramics. Transparent glass ceramics we can say is TGC. That means transparent glass ceramics are used for enhancement of luminescence properties and also develop the efficiency of solar cell by controlling the solar spectrum. So solar cell mainly you can use for the 1.1 electron volt is silicon. Silicon having the band gap is 1.1 electron volt. In our case, in prismodium or erbium doped glass ceramics, we can get the absorption band around at 1.1 electron volt. We can use this we can use for solar cell applications also. We can use the to control of the solar spectrum with spectral conversion of up conversion and down conversion converters. That means we can use for the down conversion emission or up conversion. That is a Stokes shifts. That is emission, Stokes emission and up conversion emission we can use. That is why we can use for the up and down converters. Next, transparent glass ceramics are possess the collective studies of glasses and crystals are potential optical materials that complete with the single crystal and glasses. So this way we can use for the different kind of rare earth doped glass, transparent glass ceramics by controlling the nucleation process, and we can use for the solar cell applications also. We can use for the different kind of transparent glass ceramics. Finally, the oxyfluoride glass ceramics containing low fluoride nanocrystals have the advantage of low phonon environment and higher solubility of rare earth elements activators with a better mechanical and chemical stability. This having the whenever the fluoride content is used for the nanocrystals in the transparent glass ceramics, automatically it will reduce the low phonon environment around the glass system. At the same time, it will highly soluble to rare earth elements and also the better mechanical and chemical stability having the oxyfluoride glass ceramics. Next, coming to the oxyfluoride transparent glass ceramics. So this is the semi 10 graph of the nanocrystals. In this 25% of volume, we can incorporate or embedded the nanocrystals from 10 to 25 nanometer size. This is the completely glass system, that is oxyfluoride glass matrix. At that time, its photon energy around 900 centimeters, less than 900 centimeters. Whenever this is embedded with the fluoride nanocrystal, for example, strontium fluoride or calcium fluoride. Whenever that is embedded with strontium fluoride content, strontium fluoride, calcium fluoride, automatically this strontium fluoride nanocrystal or calcium fluoride nanocrystal doped with rare earth elements. See here, rare earth elements. In our present case, rare earth elements we are using is prismodium 3+ ions. Whenever prismodium 3+ doped with strontium fluoride nanocrystals, this is rare earth ions, 85% of nanocrystals in the 15% of glass matrix. The complete glass matrix in this one rare earth elements. Total 85% of rare earth ions will be in the 15% of glass matrix. Automatically, this strontium fluoride nanocrystal or calcium nanocrystal form in the glass matrix. Automatically, this photon energy will be reduced. Whenever oxyfluoride glass ceramics photon energy 900 centimeters, whenever that is embedded with the strontium fluoride and calcium fluoride, automatically the photon energy will be reducing to less than 300 centimeters. That means photon energy reduced means photon energy that is around nearly less than equal to 300 centimeters. Whenever reduce this much amount, automatically optical properties or luminescence property enhancement will be takes place. At the same time, lifetime measurements also increases from glass material to glass ceramics. That is the main goal of to prepare the transparent oxyfluoride glass ceramics. Next, coming to the preparation method. So initially, that is 2 steps to prepare the glass ceramics. First step, we need to prepare the amorphous or glassy material. That is a well-known method is called conventional melt quenching technique. We need to prepare the initially glass material. That is, in our case, we are used for prismodium 3+ dopes oxyfluoride glass system. What is the composition is 41 mole % of silicon dioxide, 10 mole % of aluminum oxide, and 25.5% of lithium fluoride, and 23% of strontium fluoride, and just 0.5 mole % of prismodium dioxide. That is impurity or dopant is prismodium dioxide. That is a less concentration. That is 0.5 mole %. So we are using lot of fluoride content. That is 25.5, 23. That is totally we are using for the more in the fluoride content. That is lithium fluoride and strontium fluoride. That is why in this material we can do for the strontium fluoride nanocrystals. So this is a well-known technique, melt quenching technique. We are taking this complete chemical composition way into the optical balance. There is a batch composition. We can take 20 grams. That after taking the chemicals, we can put into the agate mortar. We have to agate mortar or ball mill also. We can use the crush the powders like a fine powder from micron size to nano size. We can grind the fine powder. After taking the fine powder, we can put into the platinum crucible. This is a platinum crucible and pour into the cover with a lid. Then this completely platinum crucible with chemical that we can put into the electrical furnace at the temperature of 1450 degrees centigrade for 2 hours duration. That is almost 120 minutes we can keep into the electrical furnace at the temperature of 1450 degrees centigrade. After melting completed, we can pour into the preheated brass mold. So after that one, you should be keeping the annealing at 400 degrees centigrade for 2 hours. After take down the room temperature, we take the glass samples. So after taking the glass sample, we can cut the small pieces as per our characterization specifics. In that one glass sample, we need to, this is amorphous material, glassy material. In this one, you need to convert into the glass material to glass ceramics. So how, after preparation of glass material, how you are converting the glass ceramics? Now we are going to discuss that one. So how preparing the glass ceramics? So initially we are prepared glass material by using the melt quenching technique. After you need to do the controlled crystallization of the base glass. That means whenever they prepare the glass to glass ceramics, we need to do the first initially we need to send for the DTA data from differential thermal analysis data measurements. You need to measure the DTA analysis By using the DT analysis data only, you need to do the, in the DT analysis, we need to measure three parameters. One is the glass transition temperature, TG. Next, we can measure crystalline temperature, TC, and also we can measure melting temperature, TM. So in some glasses, we can measure crystalline temperatures, TC1, TC2, in some other cases, TC3 also we can measure. But particularly one crystalline phase should be there. Crystalline temperature should be, at least one phase should be there. Then only we can prepare for the glass ceramic materials. So this is the diagram for the each schedule for conversion of glass to glass ceramics. So time versus temperature. This is nucleation temperature. Particularly what temperature we need to. That temperature we need to study by using of DT analysis. In DT analysis, what you are observing the how much exact temperature of crystalline temperature. In particular temperature, you need to do the nucleation or heat treatment method. Then only we can prepare the glass to glass ceramics. Next, coming to the experimental technique or methods of characterizations. So this is the first differential thermal analysis. DTA measurements is carried out by using the SDTQ 600 V8.3 volt 101 differential thermal analyzer, that is Newcastle D. The next X-ray diffraction XRD spectra were recorded by using the Smart Lab Rigaku Tokyo Japan company, that is using for copper K alpha as a radiation source. Next, transmission electron microscope. The TEM analysis were recorded by Geol TEM 2010. This is also from Tokyo, Japan, with an accelerating voltage of 200 kilovolt. Next, Fourier FTIR, that is Fourier transform infrared spectroscopy. So FTIR spectra were recorded by using the Flickr spectrometer with potassium bromide pellet technique. That is, we can use for the potassium bromide pellet as a reference technique, that you can scan the spectral range from 400 centimeters to 2400 centimeters. So we can cover the FTIR spectra. Next, absorption spectra. This absorption spectra also carried out by using the Flickr spectrometer. That is, model number is lambda 950. The wavelength range from 300 nanometer to 2200 nanometer. Next, finally, we are measuring the excitation, emission, and lifetime or decay time measurements were obtained using the Jobin Wayan Horiba Fluorolog 3 spectrometer using xenon flash lamp as a radiation source by exciting the sample with 443 nanometer. This particularly this wavelength used for the prismodium 3 plus ions. This wavelength we are using for the pumping of the laser source by the exciting the to measure the emission or lifetime measurements in the case of prismodium 3 plus ions. So all the measurements were carried out at the room temperature only. These are the experimental methods. Next, we are going to do this resultant discussion. First, initially we need to measure the DT analysis. After preparation of the glass sample, we need to measure first DT analysis, that is differential thermal analysis. By using DT analysis, we can get the TG, glass transition temperature, TC, and TX, both TC1, TC next melting temperature. So TG is 480 degree. This is the glass transition temperature from amorphous to crystalline temperature. How or what and particular temperature, how it will be converted. That is 480 degrees centigrade. TC1 655 degrees centigrade. TX2 678 degrees centigrade. Melting temperature is 857 degrees centigrade. So in this data we are getting from the DT analysis. By using DT analysis, we need to focus here in this one TX1, TX2. So this is the first crystalline peak. TX1 is ascribed to the precipitation of strontium fluoride nanocrystal. That is the first crystalline temperature shows the precipitation of the strontium fluoride nanocrystals. And the second crystallization with TX2 shows the bulk crystallization process of the glass matrix. So this is bulk crystallization, but we need crystalline process, that is 655 degrees centigrade. So we need to give the heat treatment or nucleation process at the temperature of 655 or 650 degree. In particular temperature, we need to do the heat treatment process. Then only glass material will be converted into transparent glass ceramics. So here see the XRD profile, that is XRD pattern of the glass material as well as glass ceramics. See here in particular glass ceramic, we have used the crystalline temperature is 650 degrees centigrade. That is the glass ceramic 650 degrees centigrade for duration is 2 hours. That is converted the glass to glass ceramic. This is glass nature. This is completely amorphous nature. We cannot observe any sharp peaks. Completely broad peak. That is why this is shows the amorphous nature. Next, whenever they giving the heat treatment at 650 degrees centigrade, for 2 hours. So in this case, this prepare the glass ceramic GC 2 hours. So in this case, we are observing the 3 SAR peaks. These SAR peaks mainly matched with the stanchion ferro nanocrystal. This exactly JCPDS number 98-004-1402. This is a JCPDS code number. That code well matches with the stanchion ferro nanocrystal. Now prepared glass ceramic sample of the prismodium 3 plus dopes oxyfluoride transparent glass ceramics. So both are well matched the X-ray diffraction fix. So this is mainly shows the number of narrow and relative intense peaks shows the diffraction pattern of the crystalline phase, with more intense peaks for the glass ceramics 2-hour sample, indicating the higher crystalline phase nature and are larger size of the nanocrystals. So larger size of the nanocrystals. At the same time, the analysis of the peaks reveals that the sample contains cubic structure. That is cubic of the stanchion for a nanocrystal phase, with the JCPDS standard card number is 98-004-1412. This is one of the important standard XRD profile pattern. So in this XRD pattern, we are observing that the prepared sample is well matches with the stanchion ferro nanocrystals. Next, coming to the XRD profile only, we need to calculate by using the Serrer formula. By using the Serrer formula, we can calculate the crystal nano size, how much crystal size will be there. So by using the DHKL, this lattice parameter HKL, by K lambda by beta cos theta. So DHKL is the crystal size in the vertical direction of the HKL lattice. Next, lambda is the wavelength of the X-rays. Theta is an angle of diffraction. Beta is the full width of measure. Beta is the each and every. Suppose this is the peak. In this peak, we need to take this how much intensity this off. So this is called full width of maximum. By using this one, we need to calculate the beta is the full width of maximum of the diffraction peak. K is the constant value 0.90. This is the copper K alpha value. Next, the average size of the particular study. We can study the nanocrystal size have been determined using the above formula, that is Serrer formula using. We can get the for nanocrystals glass ceramics 2 hours. That is, we are observing the crystal size is 34 nanometer. By using this formula, we have calculated the prismodium 3 plus dope oxyfluoride transparent glass ceramics having the each and every particle nano size is 34 nanometers. Next, coming to the TEM analysis. In TEM analysis also we used to morphology as a measurement we can study. In morphology analysis only we can know the what are the exact crystal size. In XRD also we can use it by using theoretically we are measuring. Here experimentally what is the exactly crystal size, particle size how much. By using the TEM transmission electron microscopy, that is 0.5% mole percentage of prismodium 3 plus doped glass ceramics, it can be seen that the most of the particles are in clusters. Here some will be completely arranged to formed as a clusters. Uniform size and few particles are agglomerates by using the, that is with the irregular shape. The agglomerates observed may be due to the alcohol usually dispersion powder. Whenever we are taking the glass ceramic sample, after that we crushed into the fine powder. That powder should be dispersed into the powder during TEM analysis. We can use the alcohol. That is why that agglomeration or clusters will be formed due to the alcohol dispersion by using the powder sample. That's TEM analysis. The few particles shows nano-sized elliptical-like morphology with an average particle size in 36 nanometer. In theoretically, we are getting 34 nanometer by using the XRD pattern. In TEM analysis, we are getting 36 nanometer. Almost both are similar. That is well matched with the XRD profile as well as TEM analysis. So each and every particle size prepared prismodium 3 plus doped oxyfluoride transparent glass ceramic crystal size should be in the order of 34 to 36 nanometers. So in that range only we are getting nano size. So this is the selected area. This after we are studying this one, the SCAD pattern. SCAD pattern means selected area electron diffraction. In this pattern shows that the concentrated, it will form the rings, different kind of rings. How many peaks we can observe that the insert shows the figure. So all the diffraction rings can be identified as the cubic structure and is considered with the XRD pattern. So each and every concentric rings will be well matches with the XRD pattern. That is why our prepared sample TEM analysis and X analysis well matches. So finally you are getting the our prepared nanoparticle crystal size should be in the order of nanocrystal. Transcription nanocrystal size will be in the order of 34 to 36 nanometers. Next, coming to the FTIR profile, Fourier transform infrared spectrometer. By using the FTIR analysis, we are comparison the glass and glass ceramic. See here wave number versus transmittance, that is percentage. See the glass sample and glass ceramic sample. See glass sample and glass ceramic, we observe in the FTIR analysis. In this FTIR analysis, highest intense band shows the phonon band, that is the vibrational energy phonon band. So glass and glass ceramics will be, it will be slightly band energy will be shifting. See 968 centimeter to 1000 centimeter. In glass, it's having the vibration energy, phonon energy is 1000 centimeter inverse. But in the case of glass ceramics, that is glass ceramic is GC 2 hours, that means 650 degrees centigrade. Nucleation time is 2 hours. In that one, that is decreased 968 centimeters. That means phonon band is decreased from glass to glass. That means it shows the enhancement of luminescence properties we can study by using the phonon band also. That is FTIR spectra. We are analyzing the phonon band. See here the maximum intensity vibration band in FTIR spectra is considered to be phonon energy. So this among the FTIR analysis, which band will be getting maximum intensity. In particularly 1, 2, 3, 4, 5 bands are observed. Among the 5 bands, we are observing highest maximum intense band is at, in the case of glass sample, 1000 centimeters. In the case of glass ceramics, 968 centimeters. That is slightly decreasing from 1000 to 968 centimeters. That is the host glass, which is decreased from, shifted from 1000 degrees centigrade to 968 centimeters from the glass to glass. So this is decreasing of phonon energy from 1000 to 968 centimeters. That is shows the, therefore the decreasing of phonon energy from the glass to glass ceramics due to the formation of transition fluoride nanocrystal in the glass ceramic sample, and in turn and it will be turned to enhance the luminescence properties in the present transition fluoride transparent glass ceramics. So whenever the phonon energy will be decreasing, automatically optical properties or luminescence properties enhancement takes place. So that we are going to study in the by using of FTIR analysis. Next, coming to the absorption spectra. So from the absorption analysis, we are observing the glass sample as well as glass ceramics. In the glass sample, this completely transparent glass is observing. Next, in glass ceramics also, we are observing transparent glass, that is 650 degrees centigrade for 2 hours. Since absorption spectra exhibits 6 absorption bands in the glass and glass ceramics, which are assigned to the transition from the ground state 3H4 to different excited state levels. So absorption spectra frequency glass is completely transparent, but glass ceramic 2 hours is decreasing transparent, slightly decreasing. See this glass highly transparent. After preparing the glass ceramics for 2 hours, is slightly decreasing transparency. See lossing of transparency because scattering glass is there more. So that is whenever the refractive index, if you check means it will be some difference will be there. That is why due to the scattering, this transparency will be decreasing. If you go for more than 2 hours, 3 hours or 4 hours means completely it will turn to the completely opaque nature, that is turbid nature, completely from transparent glass ceramics to turbid nature, opaque nature. That is we are observing by using the absorption spectra. See therefore the present glass ceramic sample baseline shift mainly due to the enhanced scattering loss resulting from the formation of transition fluoride nanocrystal in the glass matrix, then the reflection loss. So the reflection loss way, that is why the transparency will be decreasing, even increasing the nucleation time 2 hours, 3 hours, 4 hours means automatically that transparency will be lost. That is mainly due to the scattering effect of the refractive index. Next, coming to the absorption, by using the absorption spectra only, we are measuring the JO parameters, means Jude of light intensity parameters, that is calculated by using the JO3, that is reference number cited in the last slide, that is Jude of light intensity parameters. 7 and 8 references used to calculate the JO parameters, that is omega 2, omega 4, omega 6 values. They measured the intensity parameters for glass as well as glass ceramics. These are the present prismodium 3+ dope, oxyfluoride, transparent glass ceramics. In particularly glass ceramics intensity parameters value, omega 2 is 0.18 in 10 power minus 20 centimeters square, omega 4 is 3.83, and omega 6 1.1. See here, omega 4 is greater than 2, omega 6 greater than 2, omega 2. See higher value you are observing omega 4 intensity values. So in this value we are observing higher compared to omega 2 and omega. This is shows the indicates that the the higher rigidity and higher covalency around the prismodium 3 plus doped glass environment and surrounded by the ligand elements. So that is the mainly source the highly rigidity and covalence bond in the particularly in the case of prismodium 3 plus doped oxyfluoride transparent glass ceramics. Next, coming to the excitation spectra. From the excitation spectra, we are observing the from ground state to different excited states. See here the emission monitoring at 643 nanometer in the case of prismodium 3 plus ions. This excitation spectra. In that we are getting the three excitation bands. One is from ground state to excited state 3H4 to 3P2, 3P1 and 3P3. These are the three bands. Particularly in this case, we are observing the wavelengths 444, 468, 480. Among the three excitation bands, we are most little bit intense excitation band at 444 nanometer. This band used to pump the emission spectra analysis. We are using the 444 nanometer to pump the emission analysis. That is, we are saying the strong excitation band at 444 nanometer. For that is the transition is 3H4 to 3P2. This is used to investigate the emission spectra characterization for the present doped prismodium 3 plus doped glass and glass ceramics. So this is the emission spectra of the prismodium 3 plus doped oxyfluoride transparent glass mix. This time we are pumping the 444 nanometer and we are observing the different emission channels as well as glass and glass ceramics. In this we are getting the different regions. One is transition from the 1D2 to 3H4 excited state to ground state 602 nanometer. This is red region. Other one is 3P2 3H4 and also orange. This is orange region, this is red region and this is red region. Among these all emission bands, particularly we are getting the intense emission band is 3P2 3F2. That is the intense band at around 612 nanometers. So these are the emission analysis for the prismodium 3 plus doped oxyfluoride glass ceramics. Moreover, the enhancement of the visible luminescence intensity in the glass ceramics might be smaller difference in ionic radius between the trivalent prismodium 3 plus 0.99 angstrom ions is strontium fluoride is 1.13 angstrom ions. That is the glass ceramics containing strontium fluoride. That means this is shows the ionic radius between the prismodium 3 plus and strontium fluoride SR2 plus almost similarly equal, well matches. Prismodium ionic radius is 0.99 angstroms, is 1.13, almost equal. That is why the enhancement takes place for the luminescence properties as well as lifetime measurements. So from emission spectra only we are measuring the emission parameters, that is peak emission wavelength, effective bandwidth, delta effective nanometer and decay time measurement, T experimental as well as emission cross section. That is very important. Emission cross section will be very important for the laser parameter to study for the prismodium 3 plus doped glass and glass ceramics. So emission spectra analysis carried out by using the sigma emission formula. The full width of measurement we are using to delta effective wavelength. So branching ratio we are measuring the each and every emission peak under the emission area of the emission peak. So in this one we are calculating the delta effective value, tau experimental, stimulated emission cross section value. So in the particularly glass and glass ceramics value, see the emission cross section value will be glass to glass ceramics is slightly increasing. That is mainly due to the enhancement of the prismodium 3 plus doped transparent glass ceramics. Next, coming to the lifetime measurements. So this is the lifetime measurements for the prismodium 3 plus doped oxyfluoride transparent glass ceramics and glass. See here the glass and glass. This is pumping with 444 nanometer. The emission mounted at 643 nanometer. This decay curves are well fitted with the non-exponential nature because each and every week will be slightly turning nature. That means not in single exponential nature. This is completely non-exponential nature. This non-exponential well fitted to by using this formula, this equation, this lifetime measurements will be carried out by using the tau average, that is A1 T1 square plus A2 T square. This is here non-exponential. That is why we are getting two parameters, that is A1 A2 T1 T2. This is non-exponential. By using this formula only we are calculating the tau experimental value. By using this formula we can calculate the average lifetime for the estimated value for the glass is 7.0 microseconds. In glass ceramics is 12.0 microseconds. That means almost 3 microseconds are increased from glass to glass ceramics. These results clearly indicate that the incorporation of prismodium 3 plus into calcium chloride nanocrystal in the glass ceramic sample resulting in the longer lifetime of the particularly in the emission wavelength, that is 3P0 level, particularly in 643 nanometer, that is mainly belongs to 3P0 emission level. From that emission level, we are pumping with 444 nanometer. We are observing the decay time measurements. So glass material having the 7 microseconds, glass ceramic shows the 12 microseconds. That is the enhancement takes place from the glass to glass ceramics. This is well fitted to non-exponential nature. Next, coming to the partial energy level diagram of prismodium 3 plus dope glass and glass ceramics. By using the energy level diagram, this is prismodium 3 plus science and versus energy. We are pumping with 444 nanometer, and NR means non-native decay takes place from excitation to different metastable levels, that is different energy levels. From energy levels, we are observing the different emission peaks, almost 495, 539, 612, 643, 710, all in the visible region we are observing different emission peaks from excited levels to different ground state levels. As seen from the figure, it is noticed that the intensities of visible emissions of glass ceramic sample several times significantly enhanced with delta 10 the precursor. That means whenever glass and glass ceramic, see the emission peaks here. This glass black one is glass ceramic. Intensity will be less. If compared to glass ceramic sample, this dotted line will be, because each and every intensity will be increasing. That is mainly due to the incorporation of the strontium fluoride nanocrystals incorporated into the glass matrix. That is why phonon energy will be oxyfluoride to glass ceramics decreasing from 900 centimeters to 300 centimeters. That is why it will be enhancement will be takes place from glass ceramics to glass. So this is the partial energy level diagram of the prismodium 3 plus dope oxyfluoride transparent glass. Finally, conclusion. So prismodium 3 plus dope transparent oxyfluoride glass ceramics containing strontium fluoride nanocrystals were synthesized and characterized by their optical, structural and luminescence properties. Next, the formation of strontium fluoride nanocrystal was confirmed by the XRD pattern as well as TEM also. By using the TEM and XRD, each and every nanoparticle, strontium fluoride nanocrystal particle size would be in the order of 34 nanometer. Next, the judo of rate intensity parameters were progressively decreases from the glass to glass ceramics, signaling that the typical change in the surrounding nearby prismodium 3 plus ions from oxide to oxyfluorides. The obtained visible emissions of prismodium 3 plus dope glass ceramics are several times enhanced than the parent glass, that is the glass nature. The decay times of the 3P0 state of the prismodium 3 plus ions in the glass ceramics is established larger than that of the glass appropriate of the doping of prismodium 3 plus ions into the lower phonon energy of strontium fluoride nanocrystals in glass ceramics. Finally, therefore, the above results clearly shows that enhanced visible luminescence properties, and it indicates that the present glass and glass ceramics could be useful for photonic device application. That means laser, amplifier, sensor, different kind of applications we can use for the prismodium 3 plus dope oxyfluoride transparent glass ceramics. These are the summary of the present study. Next, finally, references. These are the references used in the present study. In this present study is published in the Ceramic International Journal, that is the year of 2019. This is one of the my paper only. This is published in the one of the international journals, Q1 journal, that is the Ceramic International, in the year of 2018. The Joule of rate intensity parameters is by using this references used to calculate the JO intensity parameters, and that is studied for the omega 2, omega 4, omega 6 values. These are the cited references in the particularly in the present study. So next class to be continuing in the other session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.